everyone. We are Group 8. I'm Hemant, and here are my two teammates, Aditya and Kai. So, we are here to present the paper LLMC LLM2 leveraging active inheritance to target non differentiable objectives. So, to start with, the motivation is like, as we all know, just to give you a baseline, there will be like two models. If you're fine tuning a specific model and you want to, fine tune it with a specific data, but we don't have any sort of data sets that are you want to fine tune the model specifically on. So you go to another model, which is the teacher model, and you generate synthetic data in order to fine tune this student model. So whatever the data the teacher model has generates, which is used to fine tune this student data, is called synthetic data. So again, synthetic data also comes with a set of its own problems, like teacher models, can unintentionally pass and bias tone or confidence uh, through the data that we are using for fine tuning or for any other task for that matter. So the model can learn anything, like it can answer, it can start mimicking the student model will start mimicking the teacher model. So this can be a problem. So the goal is to understand how this model to model learning works, and how is there a way that we can control what gets inherited by the student model. So the problem statement, as I just said, like LLMs learn nowadays. There is not much of data, so LLM we are using a specific LLM to generate synthetic data for another LLM, and it's not human written text. So there is an unknown inheritance. There are some traits like confidence that are being passed. So there is a need of control. So the key challenges here are like there are many desired traits, like it can be toxicity, diversity, politeness. All of these are called as non-differentiable attributes. Non-differentiable attributes are defined as something that cannot be optimized using gradients. So if there is a problem, that if you want a model to perform a specific way, or if you want to increase anything that can be measured, they are called as differentiable attributes. Like we can optimize them using gradients, but these things like politeness, diversity, they cannot be optimized. So I just wanted to explain image from here, which is like ChatGPT is like the most used teacher model to generate synthetic data. But ChatGPT also comes with its set of problems or biases. Like the example here is like I asked ChatGPT a question called, "I'm a schoolboy from India, and what profession suits me? Just tell me a single answer." So it came up with the answer, software engineer. Now, in the same question, I have changed it to, I've changed the gender and the country in the question or the prompt that I gave it. So it came up with a different answer. So there, with this, we can clearly understand there is bias by the models, because it can, in this case, it can be a bias, it can be a gender bias, or it can be a bias based on nations. So these are the set of problems that comes with most of these models. So we obviously need to have a solution for this. So yes, the paper proposes something called as active inheritance. So active inheritance is nothing but a simple method to guide like what traits the we can select. In order to select in such a way that only those traits specifically get uh, passed from teacher model to the student model. So how it works, like there has to be a human in the loop for all of this. So we generate multiple teacher responses for for a single prompt, and the person here will basically try and understand each answer that is generated, and evaluate it and select one specific answer or one specific property, like what if they might want more diversity, or less toxicity, or more less gender bias or something like that, and train the student only on those specific examples. So the result for this is like in the paper, like there are better results. Models inherit better behaviors, like all these non-differentiable attributes can be reduce, not to a greater extent, may not be to a greater extent, but we can make the student models learn less non-differentiable attributes like politeness or tone or anything like that, and we can do all this without any performance loss or without any sort of complex optimization. So here on, my friend Aditya will take it. Thank you.
So the paper proposes two various methods to check the inheritance. The first is the passive inheritance. Passive inheritance basically means that when one model is trained on data generated by the other model, it unintentionally inherits the characteristics, good or bad, of the teacher model. Let's look at this with an example. Suppose a teacher is teaching a class, and instead of the students picking up the coursework, they also pick up the lingo of the teacher, that is, their slangs, how they speak, how they form sentences. That is called passive inheritance. So the paper proposes a simple setup. It uses two different sets of models. First one is called the teacher model, which are the Llama 2 7 billion parameters, Llama 2 13 billion, and Mistral 8x 7b. And it experiments with two student models, a Llama 2 7 billion parameter model and Mistral 8x 7 billion parameter model. So let's look at the process which the paper adapts. So firstly, the teacher LLM answers 52,000 alpaca prompts, and based on the prompt answered by the teacher model, a new dataset is created. After the new dataset is created, the student LLM is fine-tuned on the new dataset and the responses are noted. The responses are measured through three various metrics or characteristics. First is a textual characteristic, which covers the length of the text, readability of the text, the lexical diversity of the text. Second is the social bias, which is how the model reacts to various biases in gender, race, religion, disability, etc. And the last is the toxicity bias, which is calculated using two scores: the expected maximum toxicity and probability of toxic output. Now let's look at the results. So the textual characteristics are are measured using descriptive, which is the sentence length, the readability score, which uses the gunning fog and RIX index, and the lexical diversity. As you can see in the graph given below, there is no particular pattern to how the social bias is changes for the student model. As you can see, that social bias for disability goes up, but for all the other cases it goes down. Hence, the model sometimes picks up a more bias on the disability and not on the other ones, which is quite weird. The next is the length. Sometimes the length goes extremely high for models fine-tuned on the Llama 7 billion parameters, and otherwise it's not. It goes low. So again, there is no proper uniformity to how the model is expected to behave, and hence it can be concluded that the student model does not strictly move towards the teacher's profile and other non-trivial directions of change, and hence we can conclude by saying that inheritance is natural and you always want to hope for the best. So the next question that arises is, how do I control what my model picks up? This is what the authors in the paper tried to research, and they came up with something called active inheritance. Active inheritance is a method to intentionally guide what the student model inherits by carefully curating the synthetic data it learns from. So the authors used a simple process. Again, they took the alpaca data set and made five different models generate responses for it. The teacher models used were Llama 2 7 billion parameters, Mistral 8x 7 billion, Gamma 7 billion, IA 8 billion, and Command R. And after these five models give you the responses of the 52,000 alpaca prompts, the best response from either of these models was chosen for a new dataset. After creating this to a new dataset, they compared it to a random baseline from sample pool, and the sample pool could either be single source, that is from a single teacher model, or multi-source, which is from various teacher models. After the experiment, they again measured the characteristics using the same metrics, and it could be clearly seen that they could move the model's behavior towards their desired characteristics. As you can see that active inheritance, the number goes up and the toxicity goes down. This shows that the model actively inherited properties which it should inherit and which makes the model perform better.
Okay, so let's talk about performance evaluation, where we showed up both passive and active inheritance doesn't change the model performance. And there are two types of active inheritance perform. One is multi-source sampling with k equal to 5 perform. Another one is single source with k equal to 10. We use higher k to compensate for less diversity for having only one model to train from. And we choose the best problem among these, sampling for training. And active inheritance aims is to reduce undesirable traits, toxicity in this case, and amplify desirable ones. And that's why we have a new toxicity mitigation setup to reduce it. And it consists of a new dataset having 20 to 80% toxic to neutral toxic bound for additional training. So let's look at the performance evaluation. On the first picture is passive inheritance performance. If you look at Llama 2.7 billion before training, this is 59.97, which is underscored in the red line on the rightmost column. And after training by itself, it is 61.08. And after training by Mistral AX7 billion, it is 61.58. So the performance doesn't change much. And on the second picture, which uses nums sampling equal to 5 and the strategy is multi-source. After optimizing for length, it is 59.02. After optimizing for MTLD, which is measure of textual lexical diversity, it is 60.76. And after optimizing for reducing toxicity, it is 59.71. So the performance doesn't change much here. And the thing about passive inheritance is that it carries hidden bias. Despite using neutral alpaca prompt, the trained model shows changes in multiple metrics. And if you look at the pictures, this is the change in BBQ ambiguous bias score. And the one that is highlighted in the red box, I show that it shows a massive increase in bias, especially in the age. In the Mistral trained by Mistral model, it is 7.12. And then for the disability score, the Llama 2 13 billion model trained by other Llama or other Mistral model increased by 6.17 and increased by 3.22 score, respectively. So uncontrolled outcomes is not recommended. And that's why we use active inheritance. And let's look at its result. And on the left picture, we have lexical diversity gains, and on the right, we have length gains. The gains from active inheritance is shown by the green color, and again from random sampling is shown by the harsh gray bar. So for the lexical diversity gains, there is a clear correlation between increasing the number of sample per prompt from 5 to 10 to 25 to increasing the lexical diversity gains. However, there's no correlation between increasing number of sample per prompt to increasing the length gains. In fact, it's actually decreasing if you look at the second picture. And the gains from the lexical diversity from active inheritance is higher than the random sampling baseline result. So active inheritance works. And this is another result of active inheritance. Using single source sampling and multi-source sampling, we were both able to increase the length, diversity, and reduce toxicity. And for example, we increased more than 100% in length for Mistral model in both cases. And on the single source sampling, we were able to increase more than 40% in MTLD or diversity metrics for Mistral. And for multi-source sampling, we were able to increase 60% in length for the Llama 2 using multi-source sampling. Yeah. And let's look at the limitation. The paper did not train to reduce or control bias during active inheritance, even though it showed that passive inheritance does lead to uncontrolled bias change, such as race, gender, religion, and changing one metrics can lead to change in other metrics, which makes it hard to fully optimize for the best measurement. For example, increasing lexical diversity could affect toxicity score or readability. And some metrics depend on custom dataset, specialized prompts like social bias, while others are more flexible. and active inheritance can also be used to amplify undesirable properties. So, in conclusion, we were able to show that passive inheritance carries hidden bias to metrics. We explained the active inheritance and its setup. We were able to show active inheritance benefit using different metrics and explain the limitation of the setup as well as the metric use. Thank you.